The last part of this module is part of what I think really makes organic chemistry interesting, and that is chirality. So chirality, in order for something to be chiral, we have to have a carbon center that's attached to 4 different substituents. So in order for something to be chiral, we need a carbon center attached to 4 different, and this is the key, substituents. And so if we take a look at this central carbon right here, sometimes a chiral center is denoted with an asterisk, and we take a look at 2-bromopentane, we see, right, I have 4 different substituents. I have 4 different branches off of this carbon. I have a hydrogen, that's 1. I have a methyl group, that's 2. I have a bromine, that's 3. Right, so far all of these are different than the other branches. And then the last group I have would be, we could kind of call it this propyl group, this 3-carbon group off to the side. All of those groups are different, and because all 4 of those groups are different off of that central carbon, that makes this a chiral carbon. Chirality introduces the possibility to have enantiomers, and enantiomers are non-superimposable mirror images. And that's what makes chiral molecules slightly different. So enantiomers, they are non-superimposable mirror images. And so taking a look at a hypothetical enantiomer, right, I'll put my carbon in the center, and here's my first substituent off of carbon, it's red, and then I'll have a blue substituent up here, and I'll have a green substituent over here, and I'll have a purple substituent back here. So enantiomers are non-superimposable mirror images. So if I were to flip this through a mirror, right, and redraw this structure, my carbon is still in the center, and here's my first substituent, right? That's the mirror image of that. But now, right, my blue substituent is over here. My purple substituent would be back here, and my green substituent would be over the front. These are non-superimposable mirror images. And if we were to sit at the top and look down, right, if we were to look down this carbon-carbon bond, this red carbon bond with this substituent, right, for the first example, we would see red in the center, I would see purple and blue and green. If I were to look over here and look down, right, I'm looking down this carbon, this red bond right here, I would see that red substituent there in the middle. I would see my green up in front to that purple out to the back. And I would see the blue up to the front. So that's an example of non-superimposable mirror images. And what I mean by that is I could take this structure, copy this structure, and bring this structure over here to show you that these two are non-superimposable mirror images and what that means. So I'm going to rotate this structure so that the purple and the red line up. And so if I rotate this structure so that purple and red line up, right, you see these are non-superimposable structures. I can line up the purple and the red, but the green and the blue are offset, right? I could certainly keep rotating this. I could rotate it so that the green and the red lined up. but I would never be able to match all 4 substituents. I could only get 2 substituents to overlap as I see here. So another example of non-superimposable mirror images are your left and your right hand, right? If I'm going to draw the left hand right here, a non-superimposable mirror image, right? The mirror image of your left hand would be your right hand. They are mirror images of each other, but again, just like in the previous case, they are non-superimposable. I cannot take one image and overlap it with the other image. They will never superimpose over each other. They are non-superimposable mirror images. So that's what's important about enantiomers. They are non-superimposable mirror images of each other. They are a different 3-dimensional representation in space. So thinking about the importance of enantiomers, right, your left hand only fits in a left glove, right? It does not fit in a right glove. That's the importance of enantiomers. They have a different 3-dimensional shape, and that 3-dimensional shape is important to how drugs interact with your body, because you have 3-dimensional receptors in your body that are going to bind one 3-dimensional shape of a drug and the other 3-dimensional shape of that drug, the enantiomer, right, the right-handed version of that drug, will have no impact, or it may not bind the same receptor. So these carbons that have 4 different substituents attached, 4 different branches attached, they are inherently chiral. They are inherently handedness, that they have a left-hand version and a right-hand version. Objects that are achiral do not have that. And so an example would be this beaker here, right? If I run that beaker through and make its mirror image, those 2 are superimposable. Or a chair, for example. If I run a chair through a mirror, right, the mirror image of that chair is identical. So enantiomers are non-superimposable mirror images. And that's important in the field of drug discovery and pharmacology, because that handedness is very important in how drugs interact with your body. We have 3-dimensional receptors in our body that may only bind one-handed version of this drug, just like your left hand only fits in the left glove, and the right glove, right, does not work for your left hand. It's the same thing with drug molecules. And so here's an example of enantiomers with the 2-bromopentane that we started with. We're going to have a left-handed version and we're going to have a right-handed version of each other by flipping that molecule through, making its mirror image of the structure we started with. One, we can think of it as the right-handed version, and the other will be a left-handed version of that molecule. This came from Pasteur. So Pasteur was working with tartaric acid, and so tartaric acid is made as a byproduct during the fermentation of wine, and it'll crystallize out after that fermentation is completed. And so he was looking at these crystals of tartaric acid, and he noticed that the 2 crystals were mirror images of each other. He had this observation that they had the same structure, except for they were mirror images of each other. He didn't know the structure of tartaric acid. He didn't know the absolute stereochemistry of tartaric acid, but he hypothesized that maybe there's something to do with that structure. There's something going on in that structure where the 2 structures are mirror images of each other, and there's something a little bit different in each of those structures with respect to its 3-dimensional shape that leads to the different 3-dimensional crystal structures that he observed that tartaric acid formed. And so he put forth this idea that there must be a handedness to these molecules. There must be a slight different 3-dimensional arrangement for these molecules. He knew they were both tartaric acid and that they resulted in crystals of 2 different morphologies. And those morphologies happen to be mirror images of each other. We know of them as R and S, where R stands for rectus, or the right-handed version of the molecule. And because all left-handed people are evil, right, the left-handed version is known as S for sinister. So if you see the R or S notation, that's telling you the stereochemistry of those places. So RR tartaric acid, because tartaric acid happens to have 2 chiral centers associated with it, and both are R configuration. The enantiomer of that, so the non-superimposable mirror image, is SS tartaric acid, where the other two chiral centers now are the absolute opposite stereochemistry. Both are S conformation. And if you work in the field of biology or biochemistry, right, you'll see that as D or L notation. That is kind of used in biochem and biology to talk about chirality. In chemistry, we're going to talk about it as R or S to determine the chirality of a center. So chirality is incredibly important in the activity of a drug molecule, and it's really important in the synthesis to be able to make something enantiomerically pure and able to make one enantiomer pure over all other enantiomers. That's a problem, though, because enantiomers have identical boiling points. They have identical physical properties. They're going to have identical melting points. They're going to have identical polarity, right? Because you're just changing the three-dimensional conformation of one point. And so here's an example of that. R-limonene, which is the essence of oranges, and S-limonene. All you've done is change the chirality of this center right here. We've changed the three-dimensional representation around that carbon. They're going to have identical melting points, boiling points, right? Identical polarity. The only difference between enantiomers is, number one, how they interact with other chiral structures. So, for example, your left hand, right, interacting with a left glove versus a right glove, that interaction is different. So chiral structures interacting with other chiral structures, there's going to be a handedness to that, like a handshake, right? Think of it as a handshake. If someone puts out their right hand, you have to put out your right hand for that handshake to work, that chiralness, that handedness to work. If you throw out your left hand, it throws everything off, and there's a totally different interaction. It's the same with chirality. So chiral structures interact differently with other chiral structures based on that handedness. The other way they interact differently is how they interact with polarized light. And that polarized light, we take a light bulb that has all the different wavelengths in all different directions, and we basically run it through a filter, and this filter acts as a gate, and it only allows light that's moving in one specific direction, where basically the wavelengths of those light can pass through the filter, so all of the wavelengths of light are moving the same way, in the same phase. So that polarized light interacts with chiral structures in a different way. And so R-limonene, for example, when it's exposed to polarized light, it bends that light 97 degrees in the positive direction. The enantiomer of that, S-limonene, it interacts with light in the exact opposite way. And so that's how we know the enantiomers. If the R enantiomer moves at 97 degrees in the positive direction, the S enantiomer moves that light 97 degrees in the negative direction. So equal magnitude, opposite direction. And so that's the second way you can distinguish enantiomers. Here's another example of where this is important. So ibuprofen, you might know it as Motrin or Advil. Ibuprofen has a chiral center present. And right here is the chiral center in Advil. Here's my chiral carbon right here. I have a carboxylic acid, I have a hydrogen, a methyl group, and then I basically have the rest of the molecule. So 4 drastically different branches off that central carbon. That makes a chiral center. So it's, like I said, it's really hard to make something enantiomerically pure. It's really hard to make only one enantiomer of a molecule. And that's an area of very hot research in organic chemistry of how to do enantiomerically pure syntheses, of only making one enantiomer of a structure. It's often easier to make the mixture of enantiomers. So something that's 50-50 mixture would be a racemic mixture. It's a 50% R enantiomer mixed with 50% of the S enantiomer. So it's no longer enantiomerically pure. However, like I said, because there's a handedness to this, because your receptors have a three-dimensional shape that may interact differently with one form of the drug over the other, right? It's the same here with Aleve, ibuprofen. It's well known that the S enantiomer of ibuprofen is much better at relieving pain than the R enantiomer. That being said, your body is able to racemize or change the R enantiomer into the S enantiomer in this case. So here is not an example where we need to worry about the R and the S version. Even though the S version is better, it's had better activity profile, better at reducing pain than the R enantiomer, it's not a big deal because your body is able to convert the R enantiomer into the S enantiomer, and there really are no negative consequences of the R enantiomer of this drug. So here's another example of where chirality is incredibly important. So carvone, R and S carvone is a really interesting example. We've just changed the chirality at one position, right? I've changed the chirality at this carbon right here, right? They are non-superimposable mirror images of each other. But what's really interesting about this is that R carvone is the kind of smells like rye bread, right? It's the aroma from caraway seeds. And hopefully everyone's familiar with the aroma of rye bread or caraway seeds. It's a very strong aroma. So all I've done is change the chirality of this one carbon. I've switched it from R to S, and I go from the aroma of rye bread or caraway seeds to the aroma of spearmint. So simply by changing the three-dimensional shape of one carbon, by changing the three-dimensional arrangement, right? I didn't change any of the branches, I just changed their three-dimensional position in space. I've changed the aroma of this compound from something that smells like rye bread or caraway seeds to something that smells like spearmint. And why is this the case, right? This is the case because the receptors in our body have a handedness. They have a three-dimensional structure to them. So R carvone, you inhale that, it goes into your nose and it binds to an olfactory receptor in your nose, and it initiates a cascade that sends a signal to your brain that says, I'm smelling rye bread. Whereas the S enantiomer, it also goes into your nose, it also binds an olfactory receptor, except for it binds that receptor in a little bit different way because it's a little bit different structure. Instead of being the right-handed version, it's the left-handed version. So it binds that olfactory receptor and it initiates a little bit different cascade that sends a signal to your brain that says, I'm smelling spearmint. So it all goes back to how this drug interacts with the receptor in your body and what cascade is initiated and what that tells your brain, what are you smelling? Another example of where chirality of a molecule is important is within thalidomide. And so thalidomide was first administered as an anti-nausea drug for women in the first trimester of pregnancy. So it would limit things like morning sickness. And at the time when it was first administered in the 1950s and 60s, it wasn't known about the side effects of the drug or that the fact that there were two enantiomers of this drug with different activity. So one enantiomer was active in preventing nausea and preventing morning sickness. The other enantiomer, however, unfortunately, had the negative side effect of being a tetratogen. It prevented the development and the growth of new blood vessels, which, as you could imagine, if you're trying to grow a fetus, you're trying to grow a baby, you really need the formation of these new blood vessels. And so this resulted in women giving birth to babies that had underdeveloped arms and legs, or maybe really short arms, as a result of taking this drug. And then shortly after the drug being on the market, I think it was on the market for 4 or 5 years, it was removed as the side effects were determined and discovered, all because of changing the chirality at one position in that molecule, all because you changed the three-dimensional shape of that molecule at one position. You've changed the activity of that drug with drastic consequences in this case. So here's a question for you. Identify the chiral carbon in the following molecule, right? So a chiral carbon is a carbon that has 4 different substituents, 4 different branches off of that chiral carbon. So is it carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, or we'll even say carbon 6 or carbon 7? What carbon is the chiral carbon in this molecule? Well, if we take a look at the molecule, in order to be chiral, you need to have 4 different substituents. So we can quickly and easily eliminate a few of these choices. If we take a look at carbon 1 has 1, 2, 3 identical hydrogens. That cannot be chiral. Carbon 5 also has 2 identical hydrogens. That cannot be chiral. Carbon 6, same thing. 3 hydrogens. That cannot be chiral. Carbon 2 has 2 identical hydrogens, so that cannot be chiral. Carbon 4, we're connected to only 3 different things. I'm connected to this carbon, and then this carbon twice, so I cannot have 4 different substituents. That leaves carbon 3. So if I take a look at carbon 3, the 4 different substituents for carbon 3. Carbon 3 has this ethyl group here. That's one branch from carbon 3. Carbon 3 has this methyl group, so those 2 are different so far. I also have this hydrogen, so that's 3 different substituents. And then I have this 3 carbon group as well. So that central carbon, carbon 3, is my chiral carbon because I have 4 different branches off of this carbon. That means I have 4 different substituents, and I can have 2 different arrangements in space off of that central carbon. So the important thing from today's modules, be able to identify those key functional groups, right? We should be able to identify what is a hydroxyl group, what is an aldehyde, a ketone, an ester, a carboxylic acid, as well as naming simple alcohols, aldehydes, carboxylic acids, esters, and ketones. And the last aspect that we covered of today's module was introduction of chirality, so understanding what chirality represents and how to identify a chiral center and why chirality is important, right? It's important to the 3-dimensional structure of that molecule.